In the previous video, we were talking about the end behavior of graphs and how you can determine that end behavior from the equation of the function. Now, in this video, we're going to be talking about local behaviors. So, meaning in the middle, the function can do a few turns and cross the x-axis, and we're gonna call those points x-intercepts, and it will cross the y-axis most of the time. Actually, not all functions will, but polynomial function will cross the y-axis once, always, and that's going to result in the point um, which is called Y-intercept. And just as a reminder, the Y-intercept is always has a point with the x-coordinate 0, and then your x-intercepts have y-coordinate 0. So we'll call it B0, this is C0, and D0. Okay, so these, for example, this graph or function has 1, 2, 3 x-intercepts, one y-intercept, and it has 2 turning points. What are turning points? Turning points is where they're basically your local maximum or local minimum points. Okay, so the local maximum point is where your graph increased before reaching that point, and once it reached that point, it turned to decreasing. So the increasing interval is turning into decreasing interval. And at the local minimum or another turning point, the opposite thing happens. The graph was decreasing up to this point, and then it started increasing again. So these points are called turning points, or in calculus, you're going to call them local minimum, local maximum. So let's write down turning points, otherwise known as local minimum points or maximum points. Or another term that you will see is local extrema. So yeah, those are all the names for the same thing, the names for turning points.
So how do we find those intercepts? Here we have example where the function is written in factored form already, and we need to find the x and y intercepts. So just like with any other equation or any other function, just like with linear equations, in order to find the x and y intercepts, let's start with the y-intercept. We're gonna set x equals 0 and plug it in. So f of 0 is going to be 0 minus 2 times 0 plus 1 times 0 minus 4. Okay, what does it equal to? Well, it's negative 2, 1, and negative 4, and that's positive 8. So when x equals 0, y equals 8. So our y-intercept is a point. So we need to write it as a point with x and y-intercept. So 0, 8. Okay, what about the x-intercept? To find the x-intercept, if you remember, from Algebra 2, you set y value equal to 0. Now, in our function notation, instead of y value, we have f of x value. So it's basically f of x equals 0. So we're going to plug it in, and we have 0 equals x minus 2, x plus 1, and x minus 4. Now, how do we solve that? Well, remember the zero product property? If we have a product of a times b that equals 0, then either a equals 0 or b equals 0. In this case, we have a times b times c, so either one of these factors could be equal to 0. So that's what we're going to write. It's either x minus 2 equals 0, or x plus 1 equals 0, or x minus 4 equals 0. Either one, it doesn't matter. So if we solve each one, we're going to say it's, so when does x minus 2 equal 0? Well, obviously when x equals 2. Or when does x plus 1 equal 0? When x is negative 1. Or when x is 4. So for any of those, any one of those three values, the function value or the y value would be equal to 0. So therefore, we have 3 x-intercepts in this graph. So let's write them down. X-intercepts are, and again, those are points, 2, 0, negative 1, 0, and 4, 0. So from this, we know that our graph crosses the y-axis once at 0, 8, and it crosses the x-axis 3 times at 2, 0, negative 1, 0, and 4, 0. And I mean, it probably would be nice to arrange them from smallest to largest, but you don't have to. There is no requirement that says that you have to. And really quick, this is what the graph looks like of that function. And we see that it, 3 intercepts, negative 0, negative 1, 0, 2, 0, and 4, 0, and the y-intercept of 0, 8. And again, this is a cubic function, right? So we see that pattern where the end behavior for the cubic function, when x approaches infinity, y goes to infinity, and when x goes to negative infinity, then y goes to negative infinity as well. So everything holds. The next example we're going to consider is f of x equals x to the fourth minus 4x squared minus 45. And again, we need to determine the y and x intercepts. In this case, this is a little bit more complicated because our function is not factored. They were not as nice to us as last time. Well, let's continue. We are gonna set x equals 0 first to find the y-intercept. So f of 0 is 0 to the fourth minus 4 times 0 squared minus 45. And of course, that equals to negative 45. So our y-intercept is 0, negative 45. All right. What about the x-intercepts? For the x-intercepts, we're going to set y, or f of x, equals 0. Plug it in. We're going to have 0 equals x to the fourth minus 4x squared minus 45. So again, in order to solve this, we need to factor. And here's an interesting thing. We have tools to find zeros of linear equations and quadratic equations. We have different methods, including quadratic formula. When it comes to higher power polynomial functions, higher than second power, we don't have any tools to catch those zeros. Basically, what we do is guess and check. Except there are some exceptions to that rule. Like, for example, this equation right here, it's called a quadratic type. How do we know it's a quadratic type? Well, first of all, it's a trinomial. We have three terms, only two of which have x in them. But not only that, we have powers of x, 2 and 4. So one is twice as big as the other. That's quadratic form. We can rewrite it as quadratic by doing a u sub or u substitution. We're going to say u equals x squared. Well, if u is x squared, then what's x to the fourth? And hopefully you said it's going to be u squared. So we're going to plug in u instead of x squared and u squared instead of x to the fourth. What are we going to have? We're going to have u squared minus 4u minus 45 equals 0. So, and hopefully you see that now it became a quadratic equation. And therefore, we may be able to solve it by factoring. So I'm looking for two numbers that will multiply to 45 and add to -4. And it just happens to be -9 and 5. So we could factor it as u minus 9 and u, not y, u plus 5. Okay, now we have to substitute x squared back instead of u. That's the rule. If you substitute for a different variable, it's usually temporary. You have to go back to the original variable. And what do we have? We have, because we are looking for x anyway, not u. So that will give us x squared minus 9 and x squared plus 5. Okay, so now when you look at it, you can notice that this is the difference of squares. So it could be factored even more. So we're going to have x plus 3 times x minus 3. That will give you x squared minus 9. And then we still have x squared plus 5. Now, x squared plus 5 is not factorable. It's a prime quadratic. So we're gonna leave it as is. Okay, so now when does this happen? When does this equal to 0? When x plus 3 equal to 0, or x minus 3 equals to 0, or x squared plus 5 equals to 0? Well, it's either x equals -3, or it equals +3, or, well, let's see, here we have x squared equals -5. So for x, it should be positive or negative square root of -5. But what's the square root of -5? This is going to be an imaginary number, plus or minus root of -1 times 5. And when we extract a root of -1, this becomes positive -I root of 5, or 5 root of 5 times I. You could put I after the root. There is no like strict rules, but when you put I after the root, you have to make sure that the root does not cover it, because so it would not look like I is still under the root. Okay, so that's why it's better to put it in front. Anyway, so this is what we have. Remember, we mentioned that when a quadratic equation has irrational or complex roots, they always come in pairs, in conjugate pairs. So this is a conjugate pair. This is a positive I root of 5 and or negative I root of 5. So this is a conjugate pair. And then we also have two real solutions. And this is something that we're gonna talk about still later on, that the number of solutions actually equals to the degree of the polynomial. So if we have a polynomial of the 4th degree, then we expect 4 solutions. Not all of them are real, okay? So here we only have 2 real solutions and 2 imaginary. That means that this graph will have only 2 X-intercepts. So X-intercepts are -3, 0 and +3, 0. These two x's are imaginary, so no intercepts there. What does the graph look like? Here we have a graph of this function, and we have 2 intercepts, -3, 0, +3, 0, and one y-intercept. And how many turning points do we have? Well, we have 1, 2, and 3. 3 turning points. All right, so this video is getting too long, so we're gonna stop here, but I do want you to try to find the x and y intercepts for this function. F of x equals 2x cubed minus 6x squared minus 20x. And hint, when you're factoring it, factor out the GCF first. All right, let me know how it went.